So we'll get started now. Thanks for all for coming. If I didn't get to meet you, my name is Ashok. I'm one of the co-founders and the CEO of Integral. We are a software consulting company that brings really modern practices to the automotive and transportation industries. Today we're going to have a few talks for you about automation. I'm going to go first, and I'm going to kind of challenge automation to a certain extent. And it's going to be based a lot on kind of the work of Eli Goldratt, who is kind of the father of theory of constraints. He's got a book there called The Goal, which is kind of, the textbook on theory of constraints, and really argues towards kind of making sure you're prioritizing the resources you have, whether it's capital or the people that you have on your workforce, towards kind of the right place. So that's what we're going to talk about today. Being an engineer, being part of a software company, it's kind of second nature for us to think there should be some kind of software to automate this. And oftentimes, we'll take time off from whatever we're working to try and automate something because it's just, again, in our nature to not repeat manual steps. And a lot of the time that becomes very valuable. But sometimes the amount of effort put into automating whatever that process is doesn't necessarily outweigh the amount of value that you get or the efficiencies that you gain from the automation. And it could vary based on kind of how well defined you have that step in terms of conducting that process manually. It could be based on how much of a constraint it really is on your productivity to outweigh the kind of effort required to gain the value of the automation. So there's primarily kind of three things that we're going to talk about today. And we got kind of the electrical engineering side. That's what kind of I grew up studying. And essentially decomposing everything into systems that can be represented by an electrical circuit diagram. There's kind of the theory of constraints that I mentioned. There's a drum buffer rope, which we'll get into. And the third one is Bayesian analytics. So this helps us with kind of working in areas of uncertainty where we don't necessarily have all the answers, but we have some, and we want to use a little bit of information to predict kind of where we're going to go in kind of a larger frame. So for all of this, I'm going to use a metaphor of basically a company that makes flavored water, right? So we'll start really simple. This is a company that has some money, some capital. They invest that in raw materials and in a factory, and then they make flavored water with the factory using those raw materials. They sell it to customers, hopefully for more than what it took to do all of this orchestration, and then they make more money than they started out with. And that kind of becomes a sustainable system for this business. So the first step here is to kind of decompose the system. If you want to try and increase, kind of at the end of the day, the number of dollar signs on this side based on the number of dollar signs that you have on this side in terms of investment, right? If you look at return on investment, the term, it basically means minimizing this and maximizing what's on the other side. And in order to do that, let's look at kind of what it takes to make flavored water that our customers are going to buy. So got a bunch of raw materials, maybe some empty bottles. They go into the filler, and the filler kind of fills it with the flavored water. So that's another raw material there that you're mixing watermelon flavor today because that's what you want to sell. Those bottles now filled have caps that get placed on them, and then a label with your brand and the flavor. Maybe 6-packs or 8-packs of those are kind of put in a shrink wrap. And then those shrink wraps are put into a cartoner. The cartoner goes onto a truck, or the cartons go into a truck rather, and then they go to your customers, and the customers pay you. So understanding your system better, whatever it is kind of the first step. Breaking it down into kind of a diagram like this looks pretty similar to that circuit diagram. Allows you to kind of see how that money flows from one side of your equation to the other. This can be used, by the way, for pretty much anything where you need to make decisions. You have a limited amount of time or money or a team that you're running, and they have a limited amount of time, and you're not sure what you want to spend that time on. And starting with this is a great way to kind of help you visualize where exactly your constraints or your bottlenecks are in order to kind of make those decisions. So we'll kind of go through a few exercises of decisions next and kind of go through a little bit more. So the ultimate goal here is we sell the most number of bottles of water for the highest profit and make the most dollar signs. That's the purpose of this business here, is to make money by selling flavored water, right? So let's look a little bit more. What I do is I walk out onto the manufacturing floor. Each of these machines has a little nameplate on it that talks about the maximum speed at which that machine can make bottles. So the filler can do 840 an hour. The capper can do 720. The labeler does 780. The shrink wrapper is 800. And the cartoner does 760 an hour. Question for the audience here. After 10 hours, how many bottles can we sell? 7,200, based on the slowest machine in the line multiplied by the number of hours. It's a little bit of a trick question. You are right, assuming there are customers out there who are ready to buy every single bottle that you can make. And assuming that's correct, Amy, you're right, 7,200 is the answer. It's not 8,400 based on the fastest machine. It's the slowest machine here that actually sets the pace of how many bottles you can make, how much money you can make. Even this diagram may be a little bit simplistic because, we've identified the constraint here. And then it may be a little bit simplistic here where, you have various raw materials that need to come into play. The previous diagram had an assumption that we had an unlimited amount of raw materials as well as an unlimited amount of customers. But really, lean manufacturing, one of the key elements is to prioritize the customer and then minimize all the waste. So we want to think about what that customer is going to buy in order to determine how to make what bottles here. Especially in the case that you're making flavored water and there's multiple flavors, for example. It could be orange or lemon or watermelon or whatever that's kind of really popular amongst the customers. Having a really good sense of what they want there is ultimately going to help you drive better decisions here. And they could very well be a constraint in your system. The same thing, with the raw materials. Any questions so far? We're going to kind of tweak up the complexity of this kind of incrementally. So if you do have any questions, just raise your hand, and I can make sure to clarify. Since we're good, sometimes what we do is we build a warehouse. Because the last thing we want is when a customer comes in with a hot order saying, hey, you know what? I need 300 cartons of X, Y, or Z right now, and if you can get it over, I'll send the guy with the check. And as a business owner, you're thinking, I wish I had made kind of that many bottles of this specific flavor. But that's somewhat of a conventional form of thinking there. In kind of manufacturing, lean production kind of came in and replaced that to minimize the amount of warehouse space or inventory that you carry. In the software world, this is basically like how I visualize agile development, where we're actually thinking about what is it that the customer wants, and then looking at everything else in your system and doing the fastest way to build that. And there's two ways that we can do that. We can either build a whole bunch of features and put it in our warehouse and then hope that the customer will buy that, or we can go out and find what the customer wants and build a really finely tuned kind of system here that can change direction quickly from one flavor to another in this metaphor in order to kind of change direction, be nimble as a company, be agile as a manufacturing company to change the product that you're building or how you're delivering value. So does everyone have a better idea at this stage of kind of how to decompose a system and maybe an example that you can think about how you can use this outside of a flavored water factory? Auto manufacturing, this is probably started in auto manufacturing, and then automation kind of took over with bottles to kind of roll over with kind of bottling as well. You can think about it in any other way. So we're a startup, and our resources or the cash that we have in the bank is relatively limited. So every investment we make, we have to be really cautious about making sure that there's either kind of more things that our customers will buy, or it's going to get things through the system faster so that there's more stuff for our customers to buy. And one of the questions we were challenged with was, hey, we need to grow as a business. As a consulting company, you essentially grow through kind of having more members on your team, charging more for what you do, or having more customers. So we were kind of initially focused on making sure that we were a really high-quality team. And once we started to kind of plateau in terms of the quality we could have, the second question came about of, do we hire someone that helps us with hiring more people, or do we bring on someone that helps us with bringing on more customers? And in our case, given our system for our company, we arrived at the decision that we needed to hire a recruiter before we hired a salesperson. So we have Taylor sitting in the back, who's joined our team before a salesperson joined, because we applied kind of our constraints of the growth of our business to a model like this, and we're able to kind of predict where the biggest kind of bottlenecks or constraints were. So I'll kind of tweak it up just a little bit, because another thing I cheated on here was I went to the machines and I looked at kind of the sticker on there that said what the fastest speed of each of them is. Now, if you actually go down to the line and ask folks, why aren't we getting even 7,200 bottles in a 10-hour shift, you're going to get a variety of reasons of, well, the line goes down a lot, there's a lot of electrical problems, we have to do changeovers from flavor to flavor, and these are multiple reasons that we kind of have to kind of have to apply a little bit more reality than what the max speeds are. And that kind of brings us, now that we've talked about the theory of constraints and how to apply that, and brings us to the next step of kind of the Bayesian analysis. And what we're going to do is get some experts together and do what we call a 90% confidence interval. And essentially what that means is you talk to kind of the experts, the person who runs this, the person who runs the capper, and so on, and talk about kind of if they were to guess 10 times with a range of how many bottles the capper actually produces, what range would they be right 9 out of 10 times? Now, half of that is knowing this machine well. The other half is kind of calibrating your mind to be able to do this 90% confidence interval. But assuming that you're able to get there, there's more on this later. But assuming you're able to get these ranges, the bottleneck now kind of changes. And it changes depending on which machine's having a good day. And this real-life element to it makes it a lot harder to kind of, previously we knew, hey, the capper is a problem. If there's any investment we're doing it on the capper first. We're buying a second capper maybe so that we can get more bottles out. Now that we have the real life numbers, it's a little bit harder to know exactly where that investment should go to improve this system. And that could make a difference of selling anywhere from 4,000 to 100,000 bottles. Right? So what we do for this is we model that out. Right? And this is a quote from George Box where all models are wrong, and implicitly it's probabilistic, but some are useful. So a big part of making sure the model is useful is understanding that your system's decomposed correctly. And the second part, we can actually use Excel to make our lives a lot easier. So I'm going to zoom in here a little bit. So this is going to be shared on the Meetup link, by the way, this deck as well as this spreadsheet. So there's a lot of kind of magic that goes into just using Excel functions. And essentially, what we've done here is a few things. We've got all of the different kind of constraints on the system. We've got the range input of a lower bound and upper bound for each of the components. And then essentially, we use this a random number generator, essentially, that takes these two ranges this range into consideration and generates as many as you want. And in this case, I think we've done maybe 1,000 or so. So there's 1,000 different instances of the entire system where it looks at where, at the end of any day or any hour, during that hour, what the constraint was. And then in this case, we have the constraint here. If you are going to download this Excel spreadsheet, something to kind of note is that this is a formula in column I that is based on a linear system of constraints. In certain cases, you're going to have ranges that multiply with each other, or you have to divide one another. This is the column where you want to kind of have that formula changed out so that it can tell you what the answer is for your constraint. My email is also in here. Feel free to kind of reach out if you need any more help with it. But at a high level, what we're doing is we're looking at 1,000 different instances based on our range. We're looking at, in those 1,000 instances, what is the bottleneck or the constraint. And then what you can do is the next step of applying a pivot table that tells you in this case we did 5,000, not 1,000, but out of 5,000 instances, 3,600 times the capper was the problem. And then you can do a percentage of that too, so 72% of the time, the capper is what stopped you from making money during that instance. So if you had $100 to invest back into your line, it makes sense to automate or optimize kind of that one with 72 of those $100 and spending the rest. So I'll kind of recap this back in the deck here and kind of talk about, number one, when you think about automating a system or automating a component of a system, decompose your system to understand which of the steps you should really invest in automating first. Automating, in this case, was adding a second capper, optimizing it. Depending on what you're trying to do, it may be taking a manual process and using a machine to kind of replace what humans would have otherwise done to get an infinite amount of work from in place of what a human would take a finite amount of time to do. The second one is leveraging the experts of each part of that system to come up with that 90% confidence interval. And then it's identifying the biggest constraints and exploiting it is what the official terminology is from the theory of constraints. The second one is looking at the ones with the biggest ranges. Which of your experts have, if you look at the upper and lower bounds, which of the ones are really far apart? And that gives you, as someone who kind of owns the optimization of a system, some additional data that the ones with the widest ranges are the ones that maybe the team knows the least about. So we should at least study the most, if not optimize the most. So there's two kind of takeaways or action items that you can get from this exercise. And then the fourth and maybe most important one is continually applying feedback to this model as you perform your updates or your optimizations. So if you fix the capper, go back the next month and get the new numbers on the capper and make sure that you're not kind of working on old data and you're applying feedback loops here. So that's everything that I have. Hopefully when you think about automating or investing in some kind of software, recently Stephen and I talked to a startup that was thinking about investing a lot in a CRM, and we came up with an experiment like this for them to see how much a CRM could really increase their sales, and then making sure that the investment that goes in there is relatively proportional to the gain that they can get. So hopefully you can try and apply this model to a decision that you have to make and start by decomposing the system and then arriving at an action item from there that you feel a high level of validation about. My email as well is on the deck, so please feel free to reach out if you need any help with using it. I'd be happy to. It's something I love nerding out about. So thank you. Were there any questions about this? Al? It's a good question. It's customer relationship management. So it's essentially like a giant phone book of all of your customers and all of the interactions that you've had with your business. Salesforce.com is probably kind of one of the leading companies in there. Applying a decent amount of analytics to it can do things like predicting your customers' needs and hitting them with a push notification just before they need to replace their winter tires or something like that, based on knowing when they bought it and how much they drive and so on. So yeah, the question there was whether the spreadsheet is on Google Docs. It is. So when you get the deck and you find the link to it, you'll get access to the document. All you do is kind of make a copy, and essentially it's like forking the spreadsheet, and then you can kind of apply whatever you want to your own. How do you evaluate that your confidence interval is a 90% accuracy? Feedback is probably the most kind of accurate way of knowing that, right? If you think something's going to be within a range 9 out of 10 times, then it's trying it 10 times and seeing where the range landed. The other way is if you look up things like how to do a Fermi decomposition, there's ways in which you can kind of just use your own power of estimation and having the range wider if you need it to be. The important thing is that 90% is inside and 10% is outside, rather than kind of trying to do a catch-all where you're like 100%, or another way where you come up with only one number. If you've ever been on a software team as part of a big enterprise, you've often been told to estimate something so it can go into like a milestone chart that looks like a manufacturing kind of Gantt chart. And the truth is we're lying most of the time if we come up with one number of, yeah, that takes 6 weeks to do, trust me. Chances are it could take 2 weeks, it could take 12. It depends on a whole bunch of other things, and you can do yourself a favor by breaking them down, or kind of leaning into the uncertainty of it and just kind of managing based on probability rather than based on certainty.